All right, welcome back. So hopefully you've had some time to think about our little next time question here, the question that make you go, hmm. And so let's see what you came up with. All right, so remember, in this situation, what we have is we have a positively charged particle, which is moving in that direction, through a magnetic field, which is going in this direction. And the question I asked you, actually I asked you two questions. The first one was, is there a force that acts on this positive charge? And number two, if there is a force, in which direction is it going? So this might be a little bit confusing at first because this doesn't quite fit with what we saw last time, where the magnetic field was either at a right angle to the velocity of the charge or the current, or it was parallel. So what we saw is if the magnetic field is at a right angle to the velocity or the current, then you got a force. But if the two were parallel to each other, you got no force. Well, the trick here is to look at vector components. Specifically, the way I like to do this is I like to take a look at the components of our magnetic field relative to the velocity. So let's do that. If we break the magnetic field down into a component parallel and perpendicular to the velocity, we can see exactly what's going on here. So I'm going to use green for this so you guys can see better what's going on. You can see that there is a component of the magnetic field that is parallel to the velocity. I'll call that B with the little parallel symbol. And there's also a component of the magnetic field that goes at a right angle perpendicular to the velocity. We'll call that B perpendicular, like this. Now, from what we saw yesterday, we saw that the component of the magnetic field that is parallel to the velocity, so if we say cover this guy up, is that going to cause any force? No, it won't cause any force at all. So for the purposes of this situation, it's as if this guy right here doesn't exist. It doesn't do anything. But you can see that this component of the magnetic field is perpendicular to the velocity, so that will cause a force. So now we got to use one of our handy tricks. Now remember, if it's a positive charge, which hand do we use? Do we use the right hand or do we use the left hand? Give you a second to figure it out. It's the right hand. Okay, and don't forget our old trick that I showed you yesterday. If you have a hard time remembering this, then use the trick that I did when I was a student way back in the Bronze Age. I literally made marks on my hands like this to remember. Okay, so positive charge, right hand. Okay, and according to what we saw with the right hand rule, remember the thumb is the velocity, the fingers are the magnetic field, in this case the perpendicular component of the magnetic field, and the palm is a force which pushes. So if we set this up, we have our thumb going this way, we have our fingers, remember the perpendicular component only, going that way, and your palm pushes out towards you, and so there's going to be a force that acts on this positive charge out towards you, and remember that is represented by a circle with a dot. Okay, so in this case, what we'll see is a force that comes out towards you like that. So that's the answer to our question from last time. Okay, if you recall, last time what we were doing is we were spending a lot of time getting you used to the idea of the right hand and the left hand rule, you know, what are all the different parts doing and everything, and giving you some practice with that. And there's a video up above that you should watch before this if you didn't, which kind of reviews that. Kind of gives you a little more practice at it. So if you haven't done that, make sure that you go check that video out. Remember, you should be watching the videos in sequence so that it all makes sense. And if you have questions about that, then leave comments in the discussion thread below. Also, all of that stuff was talking about the direction of the magnetic force. Well, okay, what about the amount of the magnetic force? What about the magnitude? Okay, well, if you've watched the videos before, you know what some of the equations are. But what I want to do is I want to I want to be able to look at this in two different contexts. Okay, so first thing is you probably saw a video above where they were talking about if you have a freely moving charge, okay, a charge which is freely moving through space, like an electron moving through an electron tube, or in the particular case of this positive charge flying along. Then the force that acts on this is given by QVB, right? Okay, so let me just write that down as a way of reminding ourselves. Now, for the AP students, remember from the video above, this gets us into the idea of the cross product and all that sort of stuff. If you're not an AP student, don't worry about what I'm talking about with the cross product. But the AP students know what I'm getting at. One thing I do want to mention here, though, is remember that this magnetic field has to be the component perpendicular to our velocity, right? It's got to be this guy right here. Okay. So what we can do is we can use a little bit of trigonometry here, and we can see that this is the opposite to this angle, and so that is going to be there's going to be a sine of this angle in there, right? So what we should do is we should write sine of our angle theta in there, right? And theta, remember, is the angle between the magnetic field vector and the velocity vector. Okay. So let's suppose what you've got is you've got this. Okay. Well, remember that in the previous video you saw that there was a demonstration of thinking about this in the context of a current passing through a wire, right? This is if we have a freely moving charge. What if you have a charge such as electrons, or you can think of it in terms of conventional current too, that are confined to move through a wire in an electrical circuit, for instance? Okay, well let's mention something about that. Okay, if you stop and think about it, this is the same kind of basic idea, right? Let me get a wire here. Okay. If you have a wire such as this power cord here, and you think about charge passing through it, right? That's current, so that's moving charge, right? It's moving right along. So it's going to experience forces just like we would expect to see here. And like I said, you saw in a previous video an example of this where they had the U-shaped loop of wire with the current passing through it through the magnetic field, and you could see the wire jump around, right? So this is something that is the real deal. This is also the basis for how electrical motors work. Okay, more on that later. So the idea here is how do we go from this kind of a calculation to a calculation where we have a current passing through a wire in a magnetic field? How do we calculate the amount of force that acts on the wire under those circumstances? It's real easy to figure out. Okay, and this goes back to our basic definitions of how current and velocity work. Okay, so let's remind ourselves of some things that we learned previously. If you think about the basic definition of current, right? The basic definition of current is charge per unit time. That is, amps is coulombs per second, right? So if you have current here, we can say that's charge over time, which means if we solve for Q here, what we can get is we can get charge is equal to current times time. Now, likewise, we can think about velocity. Okay, so if we think about velocity, basic definition, if we're assuming there's no acceleration, which we're going to make life easy, you have the velocity is a distance, or let's in this case call it a length over time. That is, velocity is, say, the length meters over second time seconds, right? Meters per second. Now, what we're going to do is we're going to take these two expressions here, and we're going to substitute them up there. Right? Now, watch what we get when we do this. We get our force is equal to, we have I times T times V, which is L over T. And I'm running out of space, so I'll just call this B perpendicular. right? Because remember, B perpendicular here is just B sine theta. Okay, sorry for sloppiness. Okay, now, once we see this, what happens over here? Well, you can see that the two t's are going to cancel out, right? So this two t's cancel out, then what we get is we get that the force is equal to B perpendicular times I times L. Or the way I like to say it, Bill. So if you're ever having a hard time figuring out, gee, how do I calculate the force that acts on a current carrying wire in a magnetic field? Just talk to your buddy, Bill, and you've got it. Okay. And remember, just make a note that this B is the perpendicular component, in this case, to the current flowing through the wire. So one way that we can think about this is we can think about it like so, right? If you are talking about a current carrying wire, if you think about this kind of makes sense, right? If you're talking about a current carrying wire, then what we've got is we've got a force which depends upon the amount of magnetic field. Well, the stronger the magnetic field is, the more force you're going to get. Well, that just makes sense based upon the observations from the previous videos. If you think about the amount of current, well, the amount of current, if the amount of current is more, you have more charge, right? And we see up here, if you have more charge, you're going to get more force. Okay, so that kind of makes sense. Now, the length is a little bit tricky. Okay, how does the length affect things, and why does it do that? Well, think of it like this. It kind of goes back to the whole amount of charge question. Okay, if you have a wire that's just a little tiny length, let's say it's just a few centimeters like this between my fingertips here, right? Just a few centimeters, like 2 or 3 centimeters. There's only a certain amount of charge in that length of wire. And if there's not much charge, right, you're not going to get a huge amount of force. But if we have a longer length of wire like this, like a foot or two, and all of this is immersed inside of a magnetic field, okay, then there's that much more charge all along that wire. And if there's that much more charge, then, well, more charge, more force. Okay, so this is how we can kind of think of the length, right? The longer the length of wire that there exists inside of a magnetic field, the more force that you're going to get acting on that wire. Okay, so that's the basic idea. Okay, what we have is we have the force on a freely moving charge, QVD, or sometimes I like to call it QUIVM, where this magnetic field component is the one perpendicular to the direction the charge moves. So B sine theta, or B perpendicular. And if you have a current carrying wire in a magnetic field, you calculate the force by talking to your buddy Bill. And again, remember this B perpendicular here, if you're doing the trigonometry, is B sine theta, right? That's the same thing. Okay, so these are basically two different ways of calculating the same thing. It just depends upon the context. Are you talking about a charge moving through space in a magnetic field, or is your charge confined to a wire, i.e., is it a current moving through a magnetic field? A couple of closing remarks I'll make here before we get out of here for the day. I want to mention that this is the basis of how all, not only how all motors work, but this is also the basis of how electromagnets work, right? So think about it like this. If you were to take a wire like this and you start to wrap it around like so, and you can find all kinds of YouTube videos on this. If you then have it kind of in a loop like this and you pass current around that wire, you make an electromagnet. And that's a really interesting thing. It ends up that there's a magnetic field which gets driven through the center of this loop. And that's a really interesting question. Why does that happen, right? So what you're starting to see here with all of this and with things like that, and we'll explore the idea of an electromagnet later. But what you're starting to see is that there's this kind of very interesting relationship between electricity, that is charge or current flow, and magnetism, right? It ends up that these are they're not two completely separate things. They're two sides of the same coin. You can't have one without the other. And that's really cool. That's definitely something that we're going to be exploring more in the future. One more thing I want to mention. specifically with the first expression, F is equal to QVB. It ends up that this expression is very useful if you want to determine some really fundamental answers to some really fundamental questions, like what's the mass of an electron, or what's the mass of a proton? I mean, in chemistry, you probably learned this, right? Or some previous class, you know that these subatomic particles have mass, right? And you can look up the numbers, right? The mass of a proton is 1.67 times 10 to the minus 27th kilograms. The mass of an electron is 9.11 times 10 to the minus 31st kilograms. Yeah, I have these things memorized. As you can see, I have lots of books, and that's what I do. I memorize fundamental constants in my spare time. But where do those numbers come from, right? Did somebody just make them up? And the answer is no. Of course, the way that we know this has to do with magnetism. And after this video, at some point, you should watch a later video that goes into a little more detail about exactly how that works. Specifically, how do we determine the mass of an electron using a magnetic field? It's a really, really cool thing. And so I hope you enjoy it. All right, that's it for this time. Catch you next time. You guys stay safe. Go Team Physics.